Hello physics students. So in a previous video, you learned that waves can reflect. And when they reflect, we call that process reflection. The topic of this video is diffraction. It's another thing that waves can do, and when waves do this thing, we say that the waves are diffracting. So to introduce the concept, I'm going to do a demonstration, and I'm going to use myself. So right now, as I'm talking to you, you're observing me through the action of two different kind of waves. Obviously, you could see me. So the way that you're able to see me is that the light fixtures in this room are sending out light that then hits me, hits my body, my face, and then it reflects off of me and goes into your eye. Well, not really. It's going into the camera, but you're observing the camera. The camera is basically working the same way as your eye is. So light waves, you're seeing me. You're also hearing me. And the way you hear me is my vocal cords are vibrating, and then that goes to your ear if you were here. Well, today it's going to the camera. And what I've done is, today I'm not using my audio piece here. You see it's off. I'm using instead the camera's built-in microphone, which I'll verify coming here. And you see when I tap, you're hearing the tapping as if I were tapping on your ear. So you're seeing me, you're hearing me, just as if you were standing in the classroom. Now in the case of the light, there's all kinds of light that's coming off of me. Well, you see there's a little bit of red in my sweater, so little red patches. So let's focus in on the red light. The white light is coming and reflecting red to your eye, and then my voice, you're hearing it. Now what I'm going to do is I'm going to open this door, and I'm going to go outside the door and around the corner. So right now, you can't hear me. I mean, you can't see me, but you can hear me. In other words, the sound waves are reaching you, but the light waves are not. But I'm still emitting light. It's just that somehow it can't get to you. So the question is, how did the sound come through the door, make a turn, because I was up the hallway that way. It made a turn and went to your ear or the microphone on the camera. But the light did not. The light went straight in a straight line, struck over here. Now, if you came over here, I took the camera and went like this, you would see me. But over there, you can't see me, but you can hear me. So why did that happen? Why did you hear me but not see me? So the answer to that is you have to first understand diffraction, because the sound waves diffracted in this case, but the light waves did not. So let's learn about diffraction, and then also why the sound did this thing, but the light did not. So let's go to the board. So I put my wearable microphone back on, which I can verify by going like this. And when I tap the camera's microphone, you don't hear that, verifying that I wasn't playing any tricks with the sound by carrying a microphone with me out to the hall. I was really using the camera's microphone. You were hearing me through the camera's microphone. All right, so diffraction. What it is it's the bending of a wave as it passes through an opening or around a barrier. So first thing, for an opening. So diffraction, first of all, it's the bending of a wave. Any wave, light can diffract under the right circumstances. Sound can diffract under the right circumstances. If the circumstances are not right, the wave will not diffract. So what are the right circumstances for a wave to bend? These three examples show you what they are. So in the case of an opening, suppose you have the opening, as you could see here, is much greater than the wavelength. Now, what are these lines here? Imagine you're in a helicopter looking down at the ocean, and I draw a line through the crest of each wave with maybe some dye. You would see
lines like this. And then of course the crests move, the dye wouldn't because it wouldn't move with the wave. Only the energy moves, not the water or any atoms. But besides the point. So these crests are coming to here and they hit this barrier and there's like a hole in this barrier like this. Now notice this hole width, the opening, is much greater than the wavelength. This really is a symbol in math and science. When you have two greater than signs, it means not just greater, but much greater. And so the opening's much greater than. And you see here that the wave just goes through straight like this. But if the wave if the opening gets a little bit smaller and it's only greater than the wavelength, but not much, much greater, then what can happen, or what does happen, is the wave starts to, rather than going in straight lines like this, it starts to bend around the corner a little bit. In the most extreme case, if the opening is less than or equal to the wavelength, so let's suppose this wavelength is like 2 centimeters, the opening is about 2 centimeters or smaller. What happens as these crests come and they hit this opening, they bend completely and fill this whole region up. So if these were water waves, in this case, you could sit here with an inner tube, watch the waves go by, and you're floating still. In this case, you're floating here in an inner tube, and you kind of bob up a little bit because the waves somewhat curve. In this case, it doesn't matter where you are in this water, you would be bobbing up and down the same at all places because the wave bends and spreads and fills this whole region up. So what I want you to do is copy these scenarios to get this concept down, that diffraction is a bending of wave and the amount that it happens changes depending on the opening size compared to the wavelength. So go ahead and copy these notes down now. All right, so diffraction can also occur when you encounter a barrier. So let's take a look here, and it's the same idea. The bigger the barrier is compared to the wavelength, the less diffraction happens. So we got the width here, much, much greater than the wavelength, and you see there's not much bending. If these were water waves, you could be anywhere here floating in an inner tube and you will not be bobbing up and down with the waves. But if the barrier gets a little bit smaller, only greater than the wavelength, but not much, much greater, what happens is now, instead of a straight line here, if you're floating here on an inner tube, you start bobbing up and down a bit because the wave sort of curves in a little bit. And then the maximum curving or bending of the wave around the barrier is achieved when the width of the barrier is less than or equal to the length of the wavelength. And then you see that it quickly curves in, and before you know it, it's as if the barrier wasn't even here. So if you're here thinking you're going to get shielded from the wave, you're not. The wave will bend right around because the wavelength's large compared to the barrier. So again, do your best to copy these down to show the diffraction around a barrier and the fact that it occurs at different amounts depending on the smaller the barrier, the more diffraction occurs. So go ahead and copy these notes down. Now, back to our example. Why then did the light not diffract through the doorway, but the sound did? So let me erase this and draw what we saw, and then I'll explain. So give me a moment. Okay, so here we are. The diagram of the hallway, person A, that was me. Let's suppose we've got person B standing in the corner here, and then person C, where the video camera was, where you guys were, your person C. Person A is wearing a red shirt. Suppose I'm wearing a whole red shirt, and I'm talking, so I'm producing sound and light. Okay, so that then goes out of me, and person B hears and sees person A. And that's not surprising because you see the light that comes off the light fixtures bounces off my shirt, goes right to their eye. And then the sound of my voice comes out of my mouth and goes into a straight line into the person B's ear. So because of that straight line path, no surprise that person B can see and hear me. But person C, like you saw, hears A, but does not see A. So the sound does get to person C. So the sound only turned the corner and went to my ear. So the sound bent or diffracted, but the light did not. Okay, so if you haven't already, go ahead and copy these notes down into your notebook. The question is, why did the sound bend and why did the light not? Now remember in the diagrams that I just erased, they're just right above on your notes, if you take a look at them, you will see that the smaller the opening is, the doorway, compared to the wavelength, the more diffraction happens. Now when light hits or goes through the doorway, it's the same doorway, the same size as it is for the sound. So it's not the opening itself that determines the degree of diffraction. It's the comparison of the opening to the wavelength. So what we have to do is calculate the wavelengths of the two waves to really understand why the sound did indeed diffract, but the light did not. So, yeah, I guess I could do it here. So in order to calculate the wavelength of these waves, I'm going to start with this basic equation, V equals lambda times frequency. And if I solve that for wavelength, the wavelength will merely be V divided by the frequencies of the respective waves. So let me make some room. I'm going to calculate the wavelengths of the two waves. So what I've done is I've assumed STP. Remember that there's only one speed of sound on the reference table, and that's for the speed of sound in air at STP. Front cover the reference table. Where are we? Speed of sound at STP, right here. And when you go over 3.31 times 10 to the 2, which is 331 meters per second. Now, of course, in this room, I mentioned it's warmer than STP, which is 0 degrees Celsius, which is freezing. So it's not that, so it's actually a little bit faster. But besides the point, we're just going to estimate that the speed of sound, the wavelength of sound, 3.3. Now, 100 hertz, I picked that as a pretty probable frequency of my voice, somewhere in that neighborhood, 100 hertz. So there's the wavelength of sound. We're going to do the same thing for light. Let's calculate the wavelength. So we're going to use that formula. And now we need the speed, not 331, we need the speed of light. And that is also on the reference table. So light, where are we? Speed of light in a vacuum. Now I just want to point out that a lot of students confuse these, and sometimes they use this in sound problems and sometimes this in light problems. Don't do that. Make sure you use speed of light, obviously, for light and speed of sound for sound. But here it is, 3 times 10 to the 8th meters per second. I'm going to plug that in. And by the way, I also need the frequency. So what I do is, remember I said, suppose I was wearing a red shirt, and I do have red in my sweater here. So red is here in the spectrum, electromagnetic spectrum. The frequency falls between 4.8 and 3.8 times 10 to the 14th. Let's just say even 4 times 10 to the 14th hertz is the frequency of the red light coming off my sweater. So let's plug those numbers in. So there it is. Light has a wavelength, red light, somewhere around 7.5 times 10 to the minus 7th meters. Just for reference, 10 to the minus 6th is 1/1,000,000th of a meter. This is smaller than 1/1,000,000th of a meter. Light has a tiny wavelength. Sound has a wavelength of 3.3 meters, which is wider than the camera view of this chalkboard. So the sound waves coming out of my voice are bigger than this, but the light coming off my sweater is tinier than the thickness of a sheet of paper. They both go through the doorway. The doorway the width of it is about 0.92 meters. So if you look at this doorway, sound and light both go through it, but to the sound, which is over 3 meters long, this is a tiny door. It's got to squeeze through it because it's smaller than the sound wave is. But to this tiny, minuscule light wave, this is humongous. You could fit millions of waves going across, or probably like 1 million waves across the doorway for light, not even one for sound. So the same door, tiny for sound, huge for light. In fact, if you were to get a sense like how much bigger is this than the light wave, it would be like you going through a doorway that was like 1 mile wide. So that mile-wide door, huge, right? That's what it's like for the light going through that doorway. So let's summarize. So since the wavelength of sound is greater, not smaller, but greater than the width of the door, the sound does diffract, as we saw in the diagrams I erased on this board. It bends and spreads out and fills this entire classroom when it goes through that door. And that means that person C can receive it, even though it's going around a corner, and they hear person A. But okay, since the wavelength of light is much, much less than the width of the door, the light does not diffract. In other words, it doesn't bend. It goes in a straight line, so C never receives the light coming off the shirt of person A, so they cannot see person A. Okay, so if you haven't already done so, copy these notes down into your notebook. All right, so there are other examples of things we could do to show that sound more readily diffracts than light only because it has a longer wavelength. By the way, light does diffract. There's experiments in physics that you need light to diffract through, so you need a tiny opening. One of the ways they do it in a lab is they paint a piece of glass black so no light can go through. And then they take a tiny razor blade, a thin razor blade, very sharp, and they scratch the paint and imagine a razor blade cutting a piece of paint on glass. The width of that hole would be tiny. Now we've made a tiny doorway, and then the light will diffract through that opening because finally it's small enough for the light, which is tiny. So light can diffract, but most of the time it does not. Like for example, another example. So we did an opening. How about a barrier? So I'll go like this. Oh, again, I guess I got to unplug my microphone. So now we're back to the camera microphone. You see little sound, but if I go here, right? So you are hearing the camera's audio. So here I am. Now I'm talking at the camera, but if I go like this, you can't see my mouth, right? So the light coming from the light fixtures hitting my lips and going to the camera, if I go like this, it's blocked. The light cannot diffract or curve around my hand, so you can't see my mouth anymore. But I'm talking and you could hear me because the sound can diffract around, because again, the sound wave's so long. This is a tiny barrier, and it'll curve right around it like we saw in this diagram over here. But to the light, it's a huge barrier. Same thing, but the wavelength, same barrier, but to this short wavelength of light, it doesn't bend. Another thing, so I turn around, you can't see my face, but again, you can hear me. So the light coming off my face goes straight line, but the sound coming out of my mouth, it's a small opening, and those big sound waves squeeze through the opening of my mouth and they curve all the way around and fill up the whole room. So again, diffraction. Another way, one more example I'll give you, unless I think of another one, is when you do like shadows of light. So, you know, when you see the light coming off a street light and it hits my body and then you see my shadow on the ground. The reason why there's a shadow is because the light goes straight after it hits my body and hits the ground, and it never filled in the gaps. So wherever my body was, there's no light, and that black sidewalk stays black with no illumination. Or shadow puppets, right? I do this, I make like butterflies. You've seen little kids do that. Maybe you did it as a kid. Same thing, I go like this, I'm making a bird fly, so the light from a projector hits my hand, and it doesn't curve around my hand and fill in the gaps. What it does is it goes straight like a laser, well, literally like a laser, right? It goes straight, and it makes a perfect cutout of my hands, and I can make shadow puppets. So lots of examples where we have diffraction of light does not occur because of short wavelength, but sound does diffract, fill in the gaps. So again, diffraction, the bending of waves. All waves do it, any kind of wave. The matter of whether or not it does it and to what degree is a comparison of the wavelength of the wave compared to the obstacle or the opening or whatever it's trying to bend around. So that's diffraction, all concepts today, not much for calculations. I hope you enjoyed the demonstrations. I hope you enjoyed the physics in the video. I'll see you in the next physics video.